In this video, I want to look at how to handle multiple columns that have the same variable from different samples. And typically what we'll be looking at is whether or not there is a statistically significant difference between and among the different samples, whether some samples are statistically significantly different than the others in terms of their sample mean. And what we're really looking at is whether or not the population mean for the sample would be different population means or the same population mean. One of the approaches you can take to this sort of data is to look at 95% confidence intervals. Now, the particular data that I'll be looking at in this example is the distance paper airplanes have flown. It's a kind of silly example, but it illustrates the concepts very nicely. There are three different locations that these planes were flown from. One was from the balcony of the A building. The distance that the planes fly from the porch, the second floor, was recorded. Another location was paper airplanes flown inside the health center hallway. And the third location is paper airplanes flown from the balcony of the student center. Again, the distance that they fly away from the balcony being the key measurement. Now this table here that you see on the screen is actually in chapter 12. You can see that we're down in chapter 12, data exploration 12.2, and we're in the multi-columns of the same variable from different samples, and we'll be making some of these calculations here. So here I have 4 columns. Column A is distance that planes have flown from the balcony of the student center. Column B, the distance the planes have flown from the balcony, not the balcony, down the hallway of the health center. Column C are planes thrown from the balcony of the A building during the fall of 2024. And column D are paper aircraft flight distances in March of 2016, when an El Nino had shifted the way the wind works at that building. We'll be looking to see if these come from the same sample or different samples. Each column has the same variable. Each column is the distance a plane has flown in centimeters. So this is 450 centimeters, 1600, 1700 centimeters. So all 4 columns are the same variable. If the variables were different between the columns, I could not use the approach I'm going to use. If the variables are different, of course the means will be different. They're different variables. And if the variables are different, I'm looking at a different type of analysis. But in this case, all 4 columns are distances as measured in centimeters. So I'm going to start off by looking at the sample size here using the count function on column A, but I'm actually going to go a little bit long down to row 25 because I know I'm going to fill my formula across to save time, and column C goes down to row 25. This will not affect the results of the function. Autofill is almost always wrong. There's in 1% of the cases, it's the thing to do. Here it's not. It's just giving me numbers going down. That's not right. Close that. This is the average function, and I can, if I need to, type it in, or I can drag and drop it into place. The standard deviation. Then for the standard error, I can just simply say the standard D click divided by SQRT, open parenthesis, N. Use formulas and functions, such as the one you see here, to get the right answers. And they resolve rounding errors too. You don't have rounding errors if you use the functions. Don't type numbers in. 0.05, we always use a 5% alpha, a risk of a type 1 false positive error. And then n, click, -1. Little over 2, that's about where I'd expect it to be, somewhere between 1.96 and 3. So my lower bound is going to be my sample mean minus the t critical times the standard error, and my upper bound is going to be the mean plus the t critical times the standard error. And so you can see those formulas there. Check to see they look all right, and they are. So I can see that the population mean for the student center airplanes is between 657 centimeters and 938 centimeters. So this is about 6 meters, this is about 9 meters. We're talking about a distance of something on the order of 18 to 27 feet for those not used to these metric measurements. But if I scroll over, I can simply take these and bring them across, and this is then the calculation for each of the different numbers here. There's that one that goes to row 25, the A building balcony. These are the means. They are all different. And then these are the confidence intervals, the 95% confidence interval for each of these. Now, it's a bit hard when looking at all these numbers to see what it looks like. So I'm going to do something to make a picture that I can look at. I'm going to copy those guys there and point them down here and make them come up into a little formatting there. There we go. On the right, fine, bold them up, make it look nice. This will help me keep straight what I'm doing. The lower bound for the student center, that's going to be here. The mean, this is a particular layout. This will look strange. I'm going to type the mean in twice, but I'm not going to type it. I'm just going to use equals and then click on the mean. And then I'm going to do equals the upper bound, click on that. You'll notice I've doubled the mean. That's intentional. That's not an error. All I've got is lower bound, sample mean, upper bound. I can now fill that across. I know that doesn't look a lot better, but now I can select this whole area here, and I can now make a chart. I'm going to make a very special kind of chart called a candlestick chart right there. That's not quite the right way. You'll see if you look at the bottom, it doesn't make any sense. It's lower bound. So I'm going to scroll down, switch to rows and columns. Now I have something that I can look at that will help me understand what's going on. Ignore the big long title at the top. The picture is just giving me a way to look at this data visually. And what I can see is these vertical lines are the extent of the 95% confidence interval. The mean is the middle one here. You can see the mean is right there. I can make it show up like this. The mean is 475. The lower bound 337. The upper 612. So that's 337 down here, 612 up there. So it's showing me the 95% confidence interval for the population mean for each of these samples. Where these lines do not overlap the other means, you have, like in this case, there's no overlap between this line and this line. This means that you've got lower bound here of 657, you have an upper bound of 612. 612 is less than 630, 657. So there's no way that the population mean for the student center could be as low as the possible highest population mean for the health center. So these are statistically significantly separated. We're looking horizontally. These overlap each other. They're not statistically significantly separated. There's going to be no statistically significant difference between these two because the population mean for the A building balcony could be as low as 430, and the upper bound on this is 612 and goes all the way down to 475. So 430, 431 technically, is a possible population mean for the A building balcony. It's also a possible population mean for the health center. They're not separated, not significantly. The A building balcony has the same issue. It's overlapping. Its population mean could be the population mean of the health center and the A building balcony. So this is also not separated from these. Again, you have to look horizontally and come across, and you can see that the bottom of that of this of the health center hallway, the bottom of the health center hallway cuts right into this point below the mean of the A building balcony on an El Nino spring when the wind pushed the planes back towards the building. That's why this is lower down. One other thing, though, you can see is that the student center is separated from the A building balcony. That's also statistically significant, but it's not going to separate from the A building balcony. So the picture helps us sort out. The student center planes went farther, statistically significantly farther than the health center buildings and the A building balcony buildings. But it did not go farther than the A building balcony on a regular non-El Nino term. El Nino being a weather phenomenon that tends to lead to winds that push the planes back towards the building. So we can use this approach to determine whether differences are statistically significant. And this is a good way to handle multiple variables at this level. At a more advanced level, you can use your Chapter 11.2 independent samples test to test sample on sample. So, for example, I've said that the difference between the student center and the health center is significant. You can check that by typing equals the t-test of A2 to A25, comma, well, A24 technically for that one, B2 to, sorry, C, B2 to B25. That's where the data is. I have two tails. These are independent samples. So it's a type 3. The standard deviations aren't the same. The samples are not paired. And I can see my p-value is 0.001, much less than 0.05. It's statistically significant. Even if we make a correction for the fact that we're running multiple tests here, which is a more advanced topic, but in a more advanced class you worry about making multiple tests. Here, the A building, we've also said that will separate from the A building balcony at the other end there, and so you could run a t-test on that too. But the picture, when read properly, helps you understand which things can and cannot overlap. Where they overlap, they have the same possible population mean, and they're not statistically significantly different. But planes did fly farther from the student center. It's beyond the scope of the course essentially and this video to talk about why, but the critical reason is the student center is sheltered from any wind effects, and so the airplanes tend to fly a bit farther inside this enclosed atrium. They're being launched from the second story, so they fly farther than they do in the health center, because from the health center we're just launching them from ground level. On the balcony, when we're flying the planes, the prevailing wind is onto the balcony, with it being stronger during an El Nino year, so the planes usually get blown back towards the building and they don't fly as far. So the atrium provides a shielded area for the planes to fly, and to some extent there's actually a wind coming in from the library side. The way the building is oriented, the air flows through from the east side to the west side of that particular atrium. But that's a way to tackle multiple columns of the same variable. This sort of situation where you have multiple variables with the same units. You can go after these 95% confidence intervals and use those to determine whether or not the data is statistically significantly different. Thanks for watching.